Okay, so the fourth sorting algorithm we're going to take a look at is Quicksort. We have the same setup, our 10 volume history, and again we're doing an in-place sort. Here's our key idea for Quicksort. In order to sort the volumes, just pick one at random, and that one will be called the pivot. Then organize all of the other volumes so that volumes that are less than or equal to the pivot are to the pivot's left, and volumes greater than the pivot are to the pivot's right. If you've done that, then the pivot itself has to be in the correct location. Everything to the pivot's left is less than or equal to I. Everything to the pivot's right is greater than I, and so that means that volume I has to be in the correct spot. We've now subdivided our problem basically into three parts. We've got the volumes to the left of I, and then we've got I, and then we've got the volumes to the right of I. Now I is already in the correct spot, so we don't need to worry about it. And what we'll do is to quicksort the values to the left of I, and we'll quicksort the values to the right of I. If we quicksort the values to the left of I, then each one of those volumes is going to end up in its correct position. And if we quicksort the volumes to the right of I, each of those volumes is going to end up in its correct position. So this is a recursive algorithm, obviously, and when we're done, each volume will be in its correct position, and consequently the entire collection of volumes will be sorted. Okay, so perhaps the only mysterious thing going on here is how do we go about picking a pivot? Well, let's assume that the volumes are in some random order. Then in that case, we might as well choose the leftmost volume as the pivot. Okay, so we assume that the volumes are in a random order. We pick the leftmost one to be the pivot, and then we simply step through all of the remaining volumes and make sure that the ones that are less than or equal to I come ahead of all of the ones that are greater than I. When we have got these two partitions created, in order to make sure that I itself is in the correct place, all we have to do is to swap the final volume that is less than or equal to I with the volume I, and we've now completed our partition. We've got all the volumes less than or equal to I, then we've got I itself, and we've got all the volumes greater than I. And so now we can quicksort the ones to the left of I and quicksort the ones to the right of I. So, as a very quick summary of this algorithm, we're first going to partition the values into those less than or equal to I, then those greater than I. Then we're going to quicksort the left side partition and quicksort the right side partition, and we're done. So here's what the code looks like on slides 58 and 59. We have one function that accomplishes the partitioning, and then we have another recursive function that calls the partition function and then quicksorts the left and right sides. Now for this code to work as written, A has to be an ndarray so that when we quicksort the left side and the right side, these things are views that do in-place sorts rather than shallow copies. Okay, so this code as written won't work for a list because if I use the slice notation for a list, I'm going to end up getting a shallow copy passed down rather than a view passed down. Okay, I will leave you to step through this code to persuade yourself that it works, and obviously you can test it on some test data. Quicksort does have a bad worst-case scenario. If the items are already initially sorted, and this is true whether they are in ascending order or descending order, then partitioning is not really going to break things down into two roughly equal parts. Instead, what will happen is that the pivot is going to be either at the left end or at the right end, And the partition that you will have is going to be all of the remaining elements. And consequently, that ends up being an n-squared algorithm, much like insertion sort. So, to prevent this from happening, what we will do to improve this is to shuffle the ndarray before running our quicksort algorithm. In this way, because we have n items that we're sorting, but at each level in the recursion on quicksort, we're only dealing with half as many items, the depth of this recursive function call hierarchy is log n rather than n. This algorithm ends up having an order of n log n performance, which is very nearly as good as an order n performance. This is dramatically better than the order n squared performances that we had for selection sort, insertion sort, and bubble sort. The fifth sort algorithm we'll look at is called merge sort. Our setup here is similar, but not exactly the same. Once again, we have our 10 volumes of Flugelland history, and we want to have these sorted by volume number. But this time, rather than doing an in-place sort, we are going to be willing to use an extra shelf, that is some extra memory, temporarily. So what's the basic idea for merge sort? Well, we know that if you have a sorted array of j items and another sorted array of k items, that it's trivial to merge those two arrays together into a single sorted array. You only have to do j plus k comparisons of the items in j with the items in k in order to get this merge to complete. We also know that if the array only has one item in it, it is sorted and there's nothing else to do. So making use of these two ideas, if we can recursively split the n volumes that we have downward in half and half again, etc., until we get to one item shelves or arrays, we can start from those one item arrays and merge our way back upward to get a final sorted array when we're done. Now, because n is a finite number, we know that the recursion will eventually get us to one item arrays, and we know that we'll be able to get back up again to a single n item array. So at least theoretically, this will work. All right, so on slide 61, let's take a look at how we go about this. Here's our starting shelf or our starting array, the same as we've had before. And we're simply going to split this in half. Here we happen to have 10 items in the original array, so we can split it exactly into two 5-item pieces. When we have an odd number of items, we'll just arbitrarily make the left-hand side one item larger than the right-hand side. And so what we're illustrating here in this diagram is splitting on the left side all the way down to where we get two single-item arrays. Okay, so we split the array of 10 into two arrays of 5. We split the left-hand array of 5 into an array of 3 and an array of 2. We split the array of 3 into an array of 2 and an array of 1. And we split the array of 2 into two arrays of 1. Now that we're down at the bottom level on that left-hand side, let's take a look at how we merge our way back up to get to a sorted array of n items. Well, the two single-item arrays at the bottom, containing 9 and 10, are easy to merge into a sorted array of 2 items, namely 9 followed by 10. At the next level up, we have to merge that sorted array with the sorted array containing a 3. In this case, the 3 is going to come ahead of the 9 and the 10, and so we end up with a sorted array of 3 items, 3, 9, and 10. And from the right-hand branch at that same level, we end up having an array of 2 items, 1 and 7. To merge those, well, we compare these items starting from the left-hand side and working over. 3 is greater than 1, so 1 goes first. 3 is less than 7, so 3 goes next. 9 is greater than 7, so 7 goes third. And then 9 and 10 go fourth and fifth. So that gets us up to a sorted array of 5 items. And over on the right-hand side, we will have created a sorted array containing 2, 4, 5, 6, and 8. It's easy to merge those two things together into our final sorted array of 10 items, 1 through 10. So what is the big O performance for n? That is, what is the so-called time complexity for these n items? Well, it's going to take us about n splits to get down to one item arrays. And the depth of that split tree, because at each level, each split only contains half as many items as the level above, the depth of that recursive split tree is going to be log n. Starting from that bottom level and merging our way back up, we're going to end up doing about n comparisons to get ourselves back up to the top of this recursive hierarchy. So we'll get a factor of n from the merging side, plus a factor of n log n from the splitting side, and in this case the dominant term is n log n. Consequently, we end up here with an order n log n algorithm. Now, unlike the other 4 sort algorithms that we've looked at so far, merge sort is not an in-place algorithm. It does use extra memory. And so we need to compute something called the space complexity of this algorithm, which is the amount of additional memory that this algorithm is going to require. Depending on how much memory we have available on our system relative to the amount of data that we're trying to process, it may or may not be a problem to use this extra memory space. Okay, so at the first split, where we start from an n item array, we're going to end up with 2 n over 2 item arrays. And because the recursion is going to go all the way down the left branch and then start working its way back up and down to the right sub-branches and so forth, this first n over 2 part is going to be split into n over 4 plus n over 4. That n over 4 part is going to be split into n over 8 plus n over 8, etc. Consequently, the most additional memory that we're ever going to need at once is n at the first level plus n over 2 on the left-hand side of the first level plus n over 4 on the left-hand side of the second level, and so forth. And this sum works out to just 2n. We can ignore the constant 2 and refer to this as an order n space complexity algorithm. That is, given a dataset size of n, we also need on the order of that much additional space, actually twice that much additional space. Okay, so let's take a look at how we go about splitting. We're going to be working with an ndarray here, and we need to use .copy for an ndarray to make sure that we're getting a copy of part of the ndarray, not a view of part of the ndarray. We can compute a mid-index by getting the length of the ndarray and doing a floor divide by 2, so that our left-hand part of the ndarray A1 is everything up to that midpoint, and the right-hand side is that midpoint to the end. And again, we're being careful here to get copies of the left and right side of the ndarray A1 here. Okay, so we're confident that we can split this array down into single item pieces. On the merge side, A merge is going to be the array into which we're merging our left and right side sorted arrays. We're going to set up indices into the left and right sorted arrays, Li and Ri. Now initially those indices are both going to be 0 because they're going to be subscripting the leftmost item within those two sorted arrays. The ends of those arrays, actually technically one past the end of each of those ndarrays, is going to be the length of the left-hand side for left end and the length of the right-hand side for right end. Continuing with this merge function, the logic here is sort of picky and complicated, but it basically implements the kind of merging that we looked at in the diagram back here on slide 62. Okay, so while the left index has not yet hit the left end, or the right index has not yet hit the right end, if both the left and the right still contain unmerged values, then figure out which value needs to be merged next. Otherwise, if only the left-hand side still contains unmerged values, merge from the left-hand side, and else it must be that the right-hand side contains unmerged values, and so we'll merge things from the right-hand side. I'll leave it to you to step through this and to try some tests to persuade yourself that this works. Okay, so that's the merge function that assumes that it's been given a big enough target array and sorted left-hand and right-hand side arrays, and the left-hand and right-hand side arrays are then merged into a merge. On slide 67 is code that uses that merge function to complete the implementation of merge sort. So, the parameter coming in has to be an ND array. If the ND array is either empty or only has one value in it, then it's already sorted, there's nothing to do, and we simply return. Otherwise, we figure out what the midpoint is of A, and we split into left and right sides. Then we do a merge sort on the left side so that A left is sorted. We do a merge sort on the right side so that A right is sorted. And once A left and A right are both sorted, we merge A left and A right back into the single sorted array A. Okay, so like Quicksort, merge sort is also an order n log n sorting algorithm. The last sorting algorithm we're going to look at is something called counting sort. Counting sort is limited to working with arrays of integer values, where those integer values can be treated as subscripts within an array. But within this limited domain, counting sort is extremely fast. So here's the basic idea. Let's suppose that we have some array of n integer values. What we're going to do is we're going to look for the maximum and minimum values within that array. This is, as we know, an order n operation. We just scan through and look for the minimum and maximum within A. Once we have those maximum and minimum values, we're going to create another array named counts containing m items, where m is equal to the range of values between min and max. All of these counts are going to be initialized with zeros. The counts are going to keep track of how many times each value between min and max inclusive occurs in the input data array. This is another order n operation. All right, now we're going to step our way through this input array A, subscript 0 to n, or technically n minus 1, and we're going to increment the counts associated with the sub-I element of the input array A. This is yet another order n operation. After we've gone through the n elements of A, what we'll end up with is each count sub j value for j between 0 and n minus 1 is going to be the number of times that the particular value j occurs in the input array A. Okay, so finally we're going to go back through our array of counts from 0 up to m minus 1, and we're going to place count sub k occurrences of the appropriate value into sequential elements of A. Now, because there's m elements in the array counts, this is an order m operation. All right, well, that may have been a bit difficult to follow, but the point is, as far as performance, we have order n plus order n plus order n plus order m, in other words, 3n plus m, and that boils down to order of n plus m. Okay, so we have succeeded in sorting A in time proportional to the sum of n plus m, and very often this is better than the n log n performance that we would get from Quicksort or from merge sort. And in fact, the narrower the range of values is that we have in our input array A, the better the counting sort works. All right, so let's step through an example starting here on slide 71. We've abandoned our Flugelland volumes because in this case I do want to look at an array that does have some duplicate values in it. Here's our input array A. It has 10 values in it, 3, 9, 3, 2, 7, 7, 2, etc. And first we're going to scan through this looking for the minimum and maximum values. We discover that the minimum value is 2 and the maximum value is 9. Therefore, we're going to need a counts array containing 8 values. That is 9 minus 2 plus 1 values. And 0 is going to be the initial value of each of those counts. All right, now we're going to start stepping through a second time. We discover that the first item in A is 3, and so we add 1 to the index associated with that value 3. Okay, now the minimum value is 2, so the index associated with 3 is the sub 1 index. All right, so we have counted the fact that we've seen 1, 3. Then we're going to count the fact that we've seen a 9, and so the final index over here is going to be incremented. Then we're going to see a second 3, so the index for 3 is going to be incremented to 2. Then we see a 2, 2 7s, and a 2. So the 2's counter is going to be incremented twice, and the 7's counter is going to be incremented twice. And then we'll increment the 6 counter, and the 7 counter, and the 2 counter. So when we're all done, we end up observing that there are 3 occurrences of 2, 2 occurrences of 3, 1 occurrence of 6, 3 occurrences of 7, and 1 occurrence of 9 in A. All right, so that's our counts array. So we've processed from A into counts. Now we're going to process the other direction from counts back to A. Okay, because in the counts array, we see that there are 3 occurrences of 2. So we're going to put 1, 2, 3 occurrences of 2 at the beginning of A. Then we see that there are 2 occurrences of 3. So we put 2 occurrences of 3 next. There's 1 occurrence of 6, so we put 1 occurrence of 6 next. 3 occurrences of 7. And then 1 occurrence of 9. Okay, so the size of the counts in each subscript in the count array tells us how many occurrences of the corresponding value to put back into A. And we discover when we're done that the values we now have in A are the same as the values that we originally had in A, but they're sorted in ascending order. And that's really quite cool. Here on slide 73, we have the definition of the counting sort function, implementing what we looked at on slides 71 and 72. And I will leave it to you to examine and test that code. All right, that gets us to the end of our sorting algorithms. We've looked at 6. Selection sort, insertion sort, and bubble sort are all pretty easy to understand, but unfortunately are also very slow. They're all order n squared algorithms, which means that they'll blow up very quickly as n gets very large. Quicksort and merge sort, on the other hand, are order n log n algorithms, and that's almost as fast as linear performance. Counting sort is limited to only working with integers and works best if the array that you have has a fairly narrow range of integer values in it, but it gives us an order n plus m sort, which is very fast. And of course, at the beginning of this chapter, we talked about big O and the academic definitions of big O, which is an upper bound, big omega, which is a lower bound, and big theta, which is both an upper and lower bound. In industry, big O typically corresponds to the academic big theta. Now, isn't it always going to be the case that some order n algorithm is better than any order n log n algorithm? And in turn, shouldn't that always be better than an order n squared algorithm? Well, not necessarily. If we say that an algorithm is order n log n, what that tells us is that that particular algorithm slows down at a rate of n log n as n gets larger. But if each individual step in this order n log n algorithm is really slow, then it's entirely possible that you could find an order n to the fifth algorithm, which for a given small data set is way, way, way faster than the order n log n algorithm. Okay, so big O performance is a useful guide and tells you a lot about the performance of a specific algorithm, but it does not tell you absolutely, for data sets of a given size, how one algorithm is going to perform relative to another algorithm. Ultimately, you have to do a test. Okay, and so that gets us to the conclusion of week 5, and that in turn gets us to the conclusion of the material for the programming prep course.